around the world. Then we will talk about target areas for in-building system coverage at subways. We will touch on design requirements for a specific example that we have developed to illustrate best practices for subway design, which are 3D modeling, tunnels, propagation tunnels, specifically, environmental concerns that are driving the successful design of in-building systems at subways, capacity dimensioning of subways, a very important topic, and we will spend about 20 minutes going into details what gets into the capacity dimensioning and how it's done properly. Finally, we will briefly touch upon the optimum IBS solution for subways, and then we will show you some nice 2D and 3D coverage maps generated by our software iBwave design. And with the conclusion of this presentation, we will leave about 10 minutes for Q&A. So let's get started. For some of you that have seen our previous webinars on subways, these few slides will be familiar. We are recycling them now because we think it is important for introduction. Of the 5 busiest subway underground transit systems in the world, 4 are in Asia: Tokyo, Seoul, Beijing, and Shanghai, and 1 is in Moscow. Nevertheless, you see that the sheer size of annual passengers, which is between 2.3 billion and 3.2 billion, points out that there is, those systems are quite busy, and that designing for capacity is only half the story. You need to design for coverage as well, but capacity is very, very important when designing for these systems. The next slide shows the sheer scope of underground transit systems. You see that for the first 5 busy and largest underground transit systems, they have at least 300 stations, if not more, which tells you that the scope of the work when designing those underground transit systems is quite large. Imagine having to design them from scratch. You will have to go and do that for at least 292 stations, and then if not more, which is a Herculean task. What is most important for our presentation today is this slide. It basically tells you how many passengers there are per car, how many passengers per train, and how many passengers per hour. These are the average capacity values. Very important when figuring out how many subscribers there are in the train stations or in a tunnel. The record capacity per hour is in Hong Kong with 80,000 passengers. Now, what are the target areas for in-building systems for RF coverage? First and foremost, it's entry hall, which basically where we have a handoff between a macro system and an in-building system. And because the stations are underground, the entry halls are typically underground, and that means that really we don't have all that much signal overlap between macro station and in-building system. And usually that overlap is limited to the steps that are leading to the street level or escalators that are leading to the street level. At those entry halls, at large stations, what we have are restaurants and shops. And people tend to stop there before going to trains or after they complete their trip. So when they're mentioning in-building systems, we need to take into account people at entry hall as well. And then we have areas that are, connected to platforms, which is ticket booth, escalators, hallways, and stairways. They also need to be connected. Then we finally have train platform, trains themselves, cars, and tunnels. Obviously, we need connectivity there, and we need to include those areas as well. As for the trains, they're metallic mostly, and the signal propagates through windows. And that is important to understand that putting your signal, your antenna and your coaxial cable, all of them have to be in a position to penetrate through trains at the station and in the tunnel, which means penetrating through the windows. As for tunnels go, we will spend quite a bit of time on talking about specifics of propagation inside tunnels in the next few slides. But first, we are going to talk about the design requirements for RF coverage for this imaginary train station that we have in this example. Our imaginary train station has two platforms. One is for a rapid rail system, and the other one is for the regional train system. And there are another two interconnecting levels. We have trains coming at both levels, and what we need to provide is wireless mobile commercial service, 2G, 3G, and 4G. And these are provided by 4 different wireless service providers that are dominant providers in that city. Also, public safety needs to be provided, and Wi-Fi. That is at the train station. In the tunnel, Wi-Fi is not required because Wi-Fi is not mobile technology. It does not support full mobility. The Wi-Fi in itself can be provided via train Wi-Fi, but in that case, what we really have is a backhaul through a 3G or 4G network. Public safety, on the other hand, it has to have coverage in the tunnel in the worst case scenario, which does influence what you need to provide inside the tunnel and how you need to position your radiating elements. And we will go through that in a few slides. For the minimum IBS signal requirements, because train stations are deep underground, there really isn't much of a residual macro wireless signal. So these listed power levels are pretty much what you need to achieve down there. For GSM BCCH is -85 dBm. For UMTS RSCP is -85 dBm, LTE RSRP is -95 dBm, and Wi-Fi signal is -75 dBm. Now onward to best practices. First up is 3D modeling, because the signal propagates horizontally through platforms, but also vertically between platforms, and since signal overlap is not vertical signal overlap is not something that we desire for the sake of keeping SINR or C2I clean, we would like to keep that signal overlap to minimum. And because we need to design for the system as a whole, taking into account all different layers or all different platforms at the different height levels, doing the 3D modeling of this multi-level structure is essential. And here we are showing you how a 3D model of this imaginary train station looks like. You see 2 platforms, the lower one, and if you look closely, you will see that we have 2 trains that we modeled them there at train platforms. The upper one is on the top of the picture. There is a train platform there, and there is 1 train at the station. And at each platform, you have entries to tunnels. And then in between those platforms, we have escalators and hallways, and basically interconnecting between the platforms and the train station exit. So modeling this in 3D is essential to get a good picture as to what your signal is going to look like, signal overlap, signal to interference and noise ratio, etc. For 3D modeling, we need to do 3D modeling of trains, proper 3D modeling of the trains. Why? Because the signal propagates only through windows, and having a window height, length, and position that is proper is essential to assess RF coverage. 3D models of trains, they have to be included at stations and in tunnels when we are showing the propagation, how the signal propagates at a station or in tunnels. Now we go onwards to tunnel coverage. We're going to spend a couple of slides here. Now the question is, what is best for tunnel coverage? Is it Yagi antenna or is it radiating cable? Well, it all depends on what type of a tunnel you have. If we have a short tunnel with a line of sight between the entry and exit point, then Yagi antennas positioned at both ends may do the trick. If the tunnel is longer and it curves, then radiating cables are better solution. And as we said, the signal can only propagate through windows, so those radiating cables, they should be mounted at sidewall at window height, midway at window height. And those radiating cables or Yagi antennas, whatever you're deploying, should be fed by eNode B or remote unit. And those two should be positioned at the tunnel entry. So now let's take a look at the maximum, how to calculate the maximum cable length. First off, the example, the cable that we are using in this example is U-bahn RMC78, and at 1900 megahertz, it has 69 dB coupling loss 2 meters away from the cable. This is important because the cables are mounted at the side wall and about 2 meters away from it. It's about almost midway inside the train car. This cable has 6.4 dB loss per 100 meters. And if we assume that we are feeding this cable with RU that has a 40 dBm power, and if we assume negative 5 dBm target receive power, and if we assume 5 dB window penetration loss, and this figure actually was obtained from literature, then the maximum cable loss is about 61 dB. And with that in mind, we have 6.4 dB loss per 100 meters, so maximum cable length is 800 meters. So if I have one cable coming from one end and the other cable coming from the other end, and they meet in the middle, so I can cover up to 1.6 kilometers. So if a tunnel is up to 1.6 kilometers, then I can cover the tunnel with this approach. If the tunnel is longer, then I need to cascade those radix cables. What do I mean by that? Well, I connect the first 800-meter segment to the first remote unit that is at the entry point of the tunnel. And then in the end of that segment, I put another remote unit and connect to the end of the first segment. And then I connect to the beginning of the second segment at the output port of the second remote unit, or eNode B. And so on and so forth. That way I can cascade those radix cables and extend their lengths through the tunnel. Now, the downside for this is uplink noise, because uplink noise is brought to you on by those active elements, remote units. So we have to be careful with that. We have to calculate uplink signal to noise to see how much it degrades when additional remote units are added. And this is important because uplink signal to noise will affect uplink data rate. Now, multipath signal delay in a tunnel. This is something that actually, those for you that have designed UMTS or CDMA 2000 macro networks in rural areas are familiar with. This is the same problem that you had encountered when putting repeaters in rural areas along stretches of the highway. When you are connecting a repeater to the base station, you are extending the reach of that base station. And when you do that, then you increase a multipath. And then what happens is that UMTS search window needs to be adjusted. The 3GPP standard defines UMTS search window delay settings and one of the three values. The value 40 means plus minus 20 chip delay, and that is equivalent to a delay, multipath delay of 5.2 microseconds. If you have propagation through air, that is equivalent of the multipath difference of 1.56 kilometers. The second setting is 256 chip delays, which is equivalent to a multipath difference of 10 kilometers, and the last one is 2,560, which is equivalent to the multipath delay, multipath difference of 100 kilometers. This is basically your, for our purposes of the cascaded cable length. If the cascaded cable length is longer than 1.5 kilometers, then you need to set your search window at 256, providing that your cascaded cable length is less than 10 kilometers. So if it is between 1.5 kilometers and 10 kilometers, then you put your chip delay at 256. 3GPP standards also defines LT cycle prefix settings. This is a way how LT fights multipath. Cycle prefix is a transmission gap between OFDM symbols, and CP duration defines tolerable multipath delay. There are two values. The regular value, regular CP, is 5.2 microseconds, which is equivalent to 1.56 kilometers, and extended CP is 16.7 microseconds, which is equivalent to 5 kilometers. And if cascaded cable length is greater than 1.5 kilometers, then we need to use extended CP of 16.7 microseconds. Now onwards to tunnel handoff. If we connect radiating cable on each end to a remote unit or node B, then we are assuming that we have different sectors on each end of a tunnel. And if that is the case, then when they meet in the middle, they must facilitate a UE handoff between those two sectors. And it happens while the train is moving. And we must allow a repeated handoff attempts while the train is moving. And a handoff takes 2 to 3 seconds to execute, and we should allow 3 handoff attempts before the system declares that the call is dropped or unsuccessful. So let's take a look at what it means in terms of radiating cable overlap or the sector overlap. If the train is going at 36 kilometers per hour, which is 10 meters per second, and if 10 seconds is needed for handoff to be completed, then sector overlap is 100 meters. So that means that we have said that 800 meter is our maximum cable length, and then we have 2 cables, and it is 1.6 kilometers. Well, it can be 1.6. We have to allow the last 100 meters of those 2 radiating cables to overlap. So it is not 1.6 kilometers, it is 1.4, because we let 700 meters of each segment to cover their own sector, and then the last 100 of both are overlapping. The length of sector overlap mostly depends on the train speed and the number of allowed handoff attempts, but it is customary to let 3 tries, and assuming that each of them takes about 3 seconds, then 9 to 10 seconds is what you should budget for. Now finally, the topic of public safety in a tunnel. the worst case scenario is if you have a tunnel with double tracks. And if both trains, they stop in a tunnel and they're right next to each other. Even in that case, we have to have public safety coverage at both trains, inside both trains. So what needs to happen is those public safety radix cables, they need to be mounted at the opposite side of the walls of this double track tunnel. And I have shown you a picture how it looks like when it is modeled in our tool in iBwave design. You see two trains, and what you see is tracks on the bottom, and you see one cable, one radix cable on each side. So that would actually provide you a signal, public safety signal at both trains. Commercial networks, they need not plan for worst case scenario. They can have cables on one wall only. And then this is a very important topic, environmental concerns. Tunnels, they are often damp, dusty, and they are prone to frequent but short AC power outages. And because of that, all cable connections should be waterproofed, and all remote units should have a backup battery power, and power converters should be used to filter out power instabilities. Keep in mind that tunnel vibrations, they cause PIM in loose cables, so cables can be loose in tunnels, and dust also causes PIM. And most importantly, metallic objects, they cause PIM, so antennas should be kept away from metallic objects at the station, but also they should be kept away from train roof, which means if you are designing in a tunnel, do not put antenna on the top. Do not put that in a ceiling because the incoming train will cause PIM. The equipment location should be chosen with visibility and maintenance in mind, which means a small room which is accessible at all times is a better choice for equipment location than a larger room which is accessible only after hours. And also, don't forget, if rush hour commuters can see your equipment, so can late night vandals. So you need to make your equipment vandal proof for as much as you can by making it as least visible as possible. And now we're going to spend the next 15 minutes or so talking about capacity dimensioning. The first step is user profiles. We need to define a user profile for each technology, and that is done by defining the type of service, defining venue-specific average call duration in millirlings per user during busy hour, and data rates. And we have given you here an example of 5 different service types for LTE for this example. In this example, we will be focusing on LTE because of the time for presentation is just 1 hour, but you can see the examples for UMTS in our white paper that will be distributed shortly after this webinar. And all the references are also included in that white paper. So here we have given 5 different service types. We have given the duration of the call during busy hour and the data rate for each of them. It is important to understand that all subscribers at the venue will attempt to place a call of that particular length during busy hour, which means that if I have just completed checking my email, and if I spent the duration equivalent of 50 millirlings doing so, which is about close to 3 minutes, if memory serves me well, it means that I'm free to try next browsing, and then after that video conferencing and data download and then video streaming. So all of those services will be attempted during business hour by all subscribers. Some subscribers may be denied service due to the network congestion, and our goal is to calculate call rejection or blocking for every service type based on number of subscribers, call duration, and call data rate. And that's what we will be explaining how to do in the next several slides. The first step is to determine how many commuters are there and that needs to be serving by in-building system that covers the station and the incoming portion of the neighboring tunnels. We are going to assume the worst case scenario. We said that we had 2 platforms, which means that total of 4 trains can be stopped at the station. So that is the worst case scenario. We are assuming that 4 trains are at the station. Each train has 10 cars. Each car has 150 passengers, which is the limit. Also, don't forget there are people in the shops that are at the entry hall. So we are counting them as well. And we take them into account. There is a total of 7,000 commuters at the station. We also have to assume that there are trains that are coming, and we are assuming that 2 trains are approaching the station. There are another 3,000 commuters in tunnels. So total of 10,000 commuters need to be supported by this IBS that we are trying to dimension. The next step, we have mentioned that there are 4 wireless service providers. And we need to figure out of those 10,000 commuters, how many of them go to wireless service provider A, B, C, and D. The first step is to find out the subscriber penetration rate. And this is a public information. What I mean by that is that wireless service providers or operators are public companies, and they file securities exchange information every 3 months. And there they have to say we have this many customers, which presents the that percentage penetration rate. So when I say wireless service provider A has a 30% penetration rate, this is something that can be easily checked. So we have assumed 100% penetration rate means everybody at the station has a wireless device. And wireless service provider A has a 30% penetration rate. The next 2 have 25% each. Wireless service provider D has 20% penetration rate. Now, I guess a trickier part. We need to figure out the percentage of those customers that have GSM service, that are using, actually actively using GSM service, UMTS service, and LTE service. Obviously, we are not going to have very many GSM users. We have assumed 5%. Now, this is something that you actually need to get from carriers. This is not a public knowledge. They will not tell you publicly that they have 5% GSM penetration rate within their customers. That's what we have assumed. We also assumed that the rest are in between UMTS and LTE, which is 3G and 4G. Now, the exact, the exact percentage, this is just a guesstimate. UMTS for wireless service provider A is 35%, for LTE 60%. So when we have all that, for all those, for wireless service providers, we come up with a table that will give you an idea how many passengers actually we need to provide for all of those wireless service providers, for all technologies in both locations. So, as I said, our focus of this presentation is LTE. So we are going to take a look at the numbers here. Wireless service provider has to provide for about 1,260 subscribers at the station. Wireless service provider B is 963, and wireless service provider C 875, wireless service provider D 420. So we see that wireless service provider is close to 1,000 subscribers, and in our calculations we are going to assume that that we need to provide for 1,000 LTE subscribers, which is what we see for wireless service provider B. And then when we get the numbers, then we will then extrapolate that conclusion to numbers that are higher than that, such as for wireless service provider A, or lower than that, such as for wireless service provider D. So the first step for LTE capacity calculation is to establish a link between spectral efficiency and signal to interference and noise ratio. 3GPP standard defines the relationship between CQI, modulation, and spectral efficiency. This is something that is taken from the document TS 136-213, and table 7231 is shown to the right. There you see CQI index, which can go from 1 to 15, modulation types from QPSK to 64 QAM, and efficiency, which can go from very low, from 0.15 to 5.55. Efficiency in bits per hertz per second. And then, so this table does not really tell you how SANR fits into this, but the relationship between SANR and CQI, it can be obtained from vendors or from scientific papers. This table that you see here is something that we have taken from a scientific paper. So you have seen the relationship between SNR and CQI. When we combine those two tables, what we get is the table to the right, where we have CQI modulation, MCS efficiency, and SINR. This table has 15 entries. It is quite busy, and we have simplified this for the sake of providing a clear example. So we have taken 4 entries from that table. We have taken the entry for SANR of 20 and MCS efficiency of 5.55, and we have taken 2 more entries for 64 QAM modulation, 16 QAM modulation, and QPSK. This is not meant to, this is without losing the sense of general example. I'm just making this to make the point more clear and tables less busy. So this was done just for the simplicity sake. The next question is, how many physical resource blocks do we need to use for each of those different service types? First of all, what is the physical resource block? That is basically a trunk, if you will, that is used to transport the data in LT. Most of you are familiar with the notion of trunk as a voice trunk. When the voice is carried, you know, for example, in GSM, it's given 1 trunk. So 1 customer equals 1 trunk for voice. It is a similar, something similar happening in LTE. Those physical resource blocks are basically trunks that carry the data. Now, exactly how many trunks are needed for which service type is something that we want to calculate, and it is a function of the modulation. Basically, I'm going to need more trunks if I'm using a higher order modulation, which is 64 QAM. Actually, I need fewer trunks, and I need more trunks if I'm using a lower modulation type, such as QPSK. Why is that? It is because, you know, the spectral efficiency is lower for lower type modulation. So basically, the PRB data rate, physical resource block data rate, is spectral efficiency times number of the PDSCH resource elements divided by 1 millisecond. Why 1 millisecond? Because that is a duration of physical resource block transmission. And we need to calculate based on PRB data rate, which is going to be different in each range, SANR range. We need to calculate the number of PRBs per service per SANR range. Now, in range 4, which is for SANR greater than 20 dB, the PRB data rate is going to be close to 900 kilobits per second. What exactly the data rate is going to be depends on the overhead that you have in the system. But if you look into data rates required for, let's say, video streaming, which is 2 megabits per second, in that range, which is range 4, and knowing that you need to have that each PRB is about 900 kilobits per second, it means that you have to have 3 PRBs to carry that signal in that range. So if you look at the table that gives you number of PRBs, in range number 4, video streaming needs 3 PRBs. It cannot have 2.5 or 2.2 PRBs because PRBs are assigned as a whole. So it's either 2 or 3, and here we have 3. And if you look into this table, what you will see is that those services that have a higher data rate, they need more PRBs or more trunks. So that is something that can be readily seen. But those low rates, such as email, which is 100 kilobits per second, they are going to be okay with just one PRB across the board. Now, what is the LTE traffic at the station? What is LTE offered traffic? Offered traffic is basically the traffic that is attempted by all the users at the station. We know that there are 10,000 total users, but here we are focusing on wireless service provider B, and we said that we are also focusing just on LTE. And here we have 1,000 LTE subscribers for wireless service provider B. Now, having said that, what we need to do is we need to figure out, the distribution of those 1,000 subscribers according to those 4 SANR ranges. Just to remind you, range number 4 is for SANR 20 and higher. Range 3 is for SANR between 15 and 20. Range 2 is for SANR between 9 and 15, and range 1 is for SANR between 3 and 9. Now, we need to produce SANR coverage map, which you see to your right, and based on that SANR map, we can see what percentage of the signal is greater than 20%, what percentage is between 15 and 20, and so on and so forth. And this is what we have in the map as distribution entry. 10% for range 1, 20% for range 2 and 3, and 50% for range 4. The important assumption there is that we have produced this map assuming 2 sectors, 1 sector for each platform. This is a big assumption. In the end, when we see the results for capacity, we will have to make a decision whether we are okay with 2 sectors or if we need a 3rd one. Now, we know the number of subscribers in each of this range because we have assumed a uniform distribution, which means that we have assumed that they are distributed equally throughout the station, which means that if I have 50% of the station, which is above SANR of 20, then that means that 50% of LTE subscribers for wireless service provider B are going to be in that range, and that's how we get the number of subscribers per range. Now that we know that, we multiply the number of subscribers with the duration of each service call. Just to remind you, we assume that for browsing, it is 100 millierr lengths per hour, 100 millierr lengths per subscriber. So 200 subscribers times 0.1 err lengths for each equals 20 err lengths. So that's how we get the entry of 20 err length for browsing in range 2 and 3. When we sum up all the entries here, we get total offer traffic of 420 err lengths. So this is attempted traffic by those 1,000 LTE subscribers. The next step is to figure out call blockage for all those services in all the SANR ranges. So how do we do that? Well, we first need to figure out what is the total number of available trunks to us, which is the same as to say the total number of PRBs available to us. We already know what the PRB packet size is for each of those services in all those ranges. We know, for example, that email needs only 1 PRB, and video streaming, we have seen, needs between 3 and 12, depending on where you are in the station. But what is the total number? Well, for 10 megahertz, it's 500 PRBs. Why is it not 50? Well, it is 50 in each subframe. And we have 10 subframes in a frame. Okay, so 10 times 50 is 500. Now, let's pause here for a second. What does this really mean? It means that I am assigning each subscriber that is assigned in one frame will be assigned again in the next frame. What it means that there is a transmission gap that is equal to the size of a frame. So transmission gap is equal to 10 milliseconds. So my data packets are delayed by 10 milliseconds, in transmission. So that is something that to keep in mind. It is a tacit assumption when we say that the number of available PRBs in LTE frame is 500. And now all this knowledge that we have, which is the traffic for each data service, number of required PRBs for each service, and number of different data services, all that knowledge is used to calculate call blocking for n concurrent data sessions, which is per ITU recommendations. And this is taken from ITU RM 1768-1. You see those two equations. They're quite busy. I'm not going to try to decipher them for you. Look up the document and see the explanations there. But basically, BN is call blocking for each data connectivity type. And so we can have several concurrent data calls, which is important because that is what is happening here. We have a concurrent data calls at this train station. We actually have 5 different types, so that is 5 different concurrent sessions. So NCS equals to 5 in our example. Our other assumption was that there was no voice over IP calls, meaning that voice over IP was not implemented in LTE network. Then encounter blocking rate. We calculate that based on the those ITU equations, and then you see the end result. You see those call blocks or call rejections. You see the percentages. Keep in mind, as I said, 10 milliseconds is allowed gap between transmissions, and what call blocking in that sense means is that if I was not able to transmit again after 10 milliseconds, if I could not fit my subscriber in that 10 millisecond gap, then basically I did not have enough resources for him, and the call was dropped. Okay, so you can do a similar example for the gap that is equal to 20 milliseconds, which is 2 frames and not 1 frame. But for 1 frame gap, you see the numbers here, and the lowest call block is for email, which is not unusual because email, as we have seen, needed just 1 PRB, and for video streaming it is much higher because we needed more PRBs or more resources. So this is the critical statistics for you. It shows that higher data rate services require more PRBs, have a higher, greater blocking rate, and this is what you will look into when you're making a decision whether you are happy with 2 sectors or not. If you think that you can live with video streaming that has a blocking rate at, let's say, 23.5% in 10% of the area of the station, then you should be happy with this dimensioning of 2 sectors for 1,000 LTE subscribers. The last step is to calculate carried data traffic, and we have seen what is the carried data traffic? It is offered data that was not blocked. The offered data, the attempted calls that were able to go through, and the carried data traffic is offered traffic multiplied by 1 minus blocking percentage, because blocking percentage is different for each service type. We have to make another table and to calculate carried traffic for each service type per each range. In this example, total carried traffic is 398 per length. Offered traffic was 420. So based on those two, We can calculate composite call blocking, which is 1 minus carried traffic divided by offered traffic, which is 5.2%. Data usage is basically carried traffic during rush hour, and that is 150 gigabytes. And duty cycle is almost 40%, which is utilization rate of your trunks or your PRBs. So, having said that, let's move on to IBS solution. The key requirements was that all wireless service provider must be included in building system. That means that the optimum solution should be distributed antenna system. Whether it is passive or active is up to you. Keep in mind that the active system will bring about uplink noise, which passive won't. And keep in mind that you have an option of putting radiating cables inside tunnels. And that's basically it for the optimum solution. The distributed antenna system should be chosen in this case. Now let's move on to RF coverage maps. This is a tunnel, GSM coverage, 2 trains. I am showing you on the right-hand side the how it looks like when it is modeled in our tool, in iBwave design, with 2 radix cables on the side walls, and you see then a 3D view of the coverage in a tunnel and inside the trains. The next one is platform 1. The GSM coverage, you see opposite Yagi antennas at the entrance of each, well, at the end of each platform, which is also near the entry point to a tunnel. So they're pointing, toward each other. They're pointing, toward the middle of the platform. And this is also the best practice if you can do this, because you are going to be able to move away from the train top, the train roof, which is metallic object which causes spin. So if you are moving your antenna, move it to toward the platform and point directly to a platform rather than point above the train. And then you see the coverage that those 2 antennas give on that lower platform. The next one is the upper platform. We have only shown 1 train here in this example. You see that I have many more antennas because I also have another intermediate level to cover. But the principle is the same. Directional antennas are shown at the end of the platform pointing toward the middle, directing the signal toward the middle. Also, when you do that, it facilitates the handoff between tunnel and the platform. Because if you are using directional antenna, then you have a weak coverage toward the tunnel, and that is okay because at the entry of the tunnel you should have either another antenna pointing down the tunnel or radiating cable. So that way we don't have too much signal overlap. And then train station, 3D, both platforms and areas in between. You see how the coverage looks like. This is GSM signal. Here it is LTE signal. Now, remember what I told you that we had 2 sectors, 1 for each platform. You can tell by just looking at this that it is a 2-sector system because SNR is very high at each platform, and in between it is a bit lower. You see a lot of yellow and green in between those 2 reds. And maximum achievable data rate is something that can attest to it as well because it is directly tied to SANR. I see here there's lots of green and blue in between those 2 platforms. So, in a summary, what we have done today, we have talked a bit about subways around the world. We talked about target areas for IBS coverage. We talked about design requirements and best practices, covered 3D modeling, tunnels, environmental concerns, capacity dimensioning, chosen DAS as IBS solution, produced some nice 3D coverage maps, And with that, I turn over to Anna about our Q&A.
Thank you, Vladan. I hope you were all able to take away some new points from this webinar. Now we will get to some of the many questions that we received during our registration and throughout the webinar via the GoToWebinar. So, Vladan, the first question is about the use of leaky coax and their limitations.
Yes, the limitations for leaky coax, we have covered that a bit, is that we need to calculate the maximum distance that can be used, which is a function of the coupling loss and loss per 100 meters. And also is a function of what the target coverage signal level is inside the train. Once we figure that one out, that's the maximum distance of the leaky coax cable. It is important to do that for every technology and every frequency. And then once you have all those distances, you choose the shortest one. And also keep in mind that a signal overlap between sectors must exist. So if there is if there are two sectors in a tunnel, then we have to budget for a cable overlap between those two sectors, which is something that we have covered in this presentation as well.
The other question that's related to this is about the leaky cable, whether one long piece or segments is appropriate?
Yes, I would say one long piece, and the reason for that is that if you are running shorter segments, then you need to re-amplify the signal all the time, right? So, for example, if you have 800 meters, should I take 800 meters or 4 200-meter segments? If you take 4 200-meter segments, you are re-amplifying it all the time, and that is adding noise on the uplink, and then that may be a problem. So that's why I would say go with a longer piece.
And I think we can take one more. The change in radix cable pattern when metallic conduits and pipes are nearby?
Yeah, this is really not just about the change in the pattern. This is about PIM. Okay, so metallic object. Oh, keep in mind, this is what you are designing here is a neutral host system that is composed of lots of spectrum bands, right? Lots of technologies and lots of spectrum bands. So what happens there is that generating a PIM is, I wouldn't say quite easy, but is easier than if you have a fewer technologies and fewer bands. So metallic objects are going to help you generate a PIM. So putting radix cables or putting antennas near metallic objects is something that is going to not only alter their radiation pattern, but it's also going to generate PIM. So be very mindful of not to put that radiating body, be that radix or antenna, near any metallic structure.
Just one last question. We only have time for that. If two cables are running from either end of a tunnel, is of different sectors, then how much of the overlap is required at the middle of the tunnel?
Right. We have given an example here. The amount of overlap is really a function of the train speed at that section and how much time you want to give your UE to complete the handover. We have actually mentioned in our white paper, we have a reference that basically says that 2 to 3 seconds is needed for each handover attempt, but you cannot leave just that one attempt as an option. You have to let UE try 2 or 3 times before you declare that handoff attempt unsuccessful. So let's say if it is 3 handoff attempts, and then it is 3 seconds for each attempt, then 9 to 10 seconds should be budgeted, for UE to complete the handoff. Now, what is that as far as the distance goes is a function of the train speed. We have given an example when train was going at 36 kilometers per hour, which is 10 meters per second. So you have 10 seconds and 10 meters per second, that's 100 meters. So in this case, 100-meter overlap should exist between those two cables coming from either end of the tunnel.
Thank you, Vladan. We're out of time. I would like to thank everyone who joined us and for your questions. To continue the discussion, I've started a LinkedIn group at our iBwave in Building community. If you're not a member yet, I encourage you to join us. You can look for a recording and slide deck from today's presentation in your inbox tomorrow. The written case study will also be posted on our blog tomorrow. Thank you for taking the time for joining us, and I wish you a good day.